Ladies and gentlemen, my name is John Toland and I'm the director of the Isaac Newton Institute. And my words will be very few, simply to welcome you here, to welcome John Conway and Siobhan Roberts, who are going to have a conversation about the life of a mathematician. Not any old mathematician, but this mathematician. John Conway is, of course, extremely famous, especially in Cambridge circles, even though he left Cambridge in 1986.
In 85, actually.
85, which was before the Isaac Newton Institute was founded. And I think it's true that you've never been
I've been here.
participant at the Institute.
I've been here once or twice.
Once or twice.
Yeah.
Anyway.
I don't know if I've actually given a lecture or anything here at the Institute.
Our records show that perhaps you haven't, but I'm not
Okay.
sure. That's all I want to say. I'll hand over to Siobhan, who will take you through the proceedings, and we'll see how things go. Thank you very much.
Thank you very much. Well, the red light just went off on the mic. I don't know if it's working now.
It is not, I suspect.
No. Where's the technical expert? There we go. Oh, it is working. Okay, good. Just didn't see a red light. So thank you all for coming, and thank you very much, John Toland, for having us here. It's a big treat. The book came out in the US in July. The title is
July
Genius.
the 14th, Bastille Day.
Know it all. And here be the book, and it came out in the UK on September 10th. Is that a special date of any note or moment?
Well, it's just one day before September the 11th.
Indeed. So I thought first we would do a brief reading just to give you a sense of the book itself. And it'll also serve to give you a sense of what the process of being biographized was like for poor John, and also what it was like for me to be writing about poor John. So we do have your...
You're trying to get some sympathy for yourself, aren't you?
So this chapter, it's chapter 9. It's titled Character Assassination. It's about the game of life, and it's I'll just read a prologue. So all hell broke loose with respect to the game of life when Martin Gardner wrote his October 1970 column about life. In the column, Conway issued a challenge, $50 for the first person to find the piece of circuitry in the computer, the glider gun, that would all but prove life universal. And the pandemonium has continued ever since. Certainly.
Yeah, okay. They didn't have to find a glider gun. They had to find something whose population would grow indefinitely.
Mm-hmm.
And the thing they found was the glider gun.
Right. Okay. Thank you for the clarification. On a local level, when I was talking to John, researching the book, in particular talking about life, would cause pandemonium to often break out. Considerable perturbation. Without much warning, he would reach his threshold and turn testy. It terrified him that another of his worst nightmares might come true, that his life would in the end be reduced to life, capital L, life. When we met for another session in the alcove, I was at the Institute for Advanced Study in Princeton for a number of years working on the book, so I would sort of walk across town and sit myself down in the alcove at Princeton with my tape recorder in between, and John and I would talk about any number of subjects that I would raise. So when we met for another session in the alcove, John tried to prepare me for the hellish consequences, i.e. the wobbly he was about to throw.
Oh, that's me, isn't it?
Yes.
Oh, God. I don't know whether to tell you now or not. Is that roughly the tone of voice I should adopt?
Yes, you were quite
Okay.
outraged. And I said, oh, sure, get it over with.
I've got to read this nonsense now. I have a special font in the book, by the way. So anyway.
Yes, here actually is the page that we're reading. So you can see that John comes in with his own font.
Yeah. Well, it may be upsetting to you. It's upsetting to me, actually. I lay in bed probably about a week ago in the early hours of the morning, and I've decided, I have to say, that I'm becoming thoroughly disenchanted with your biography. It's basically because recently you've been asking, these questions about the life game. And do you know something? I hate the life game. I've really realized I hate the damned life game.
Well, that can go in the book.
Let me finish. So I'm scared of the following thing happened. I'm not going to read all this junk. Let me just shorten it a bit.
Okay.
Every time I turn to a new popular mathematics book, I look for a certain name in the index. And, I find it. It says pages 33 to 37, 59 to something, 107 to 121, etc. And it's all about the damned life game. And that's essentially all it says, And, okay, well, I'll go back to reading this thing. It's not character assassination exactly, it's quality assassination. I regard life as trash, frankly. It was a real part of my life to have discovered it and so on. And I don't think it should be removed or excised. It's like a cyst, actually, And it seems to be all that I'm known for among the general public. And I wanted you somehow to set the record straight by not doing the same damned thing again. I mean, God, I was quite upset. I was so terrified that I was thinking of saying, so to speak, publish and be damned. I don't want anything more to do with it.
May I speak?
No, not yet. You should appreciate something. It was never a big deal as far as I was concerned. How many people know about this life game, by the way?
Dare you raise your hand?
Oh, good. Good. I mean, it's not a great proportion of the audience. I'm so glad. Well, enough people know. I don't want to describe it. That'll make me feel worse.
Yes, we don't need to do that.
So it was never a big deal. It was just a recreation, a game we played. Somehow it became a bit more important later on, or at least it did in the eyes of other people. I never thought of it as very important. I just thought of it as a bit of fun. In fact, in a way, I felt ashamed of it even while we were studying it. We, by the way, means a bunch of graduate students here in Cambridge, and then me, and I was, a few years older than they were, junior faculty. I don't think it counts in the mathematical community, at least in the serious mathematical community. I don't think any of my Princeton colleagues think this life game is of any importance. I don't know, and in a way it doesn't count for me. Yes. Well, I'm going to sort of cut this thing. So how can I say it? Life was a genuine part of my, that's big life, capital L life, was a genuine part of my life, my little life. Actually, it's quite a long life now. And I've told you about, I haven't told you about the Jugendtraum,
right,
and so on. But really, I want you to minimize it rather than maximize it. Okay, now you can speak.
Well, I sort of took the strategy at that point in that particular interview session that the less said, the better, and I think we moved on to other subjects. But that just gives you a taste of the book. It's sort of this double narrative between myself setting up the history to some degree, telling a few stories, and then every so often John comes in with your special font and picks up the narrative thread, and we sort of pass the baton back and forth. And primarily I decided to do that because, John, you're famous for being an expositor and a teacher and a popularizer, as well as a storyteller, a masterful storyteller. So I felt there was very little to be gained and indeed a lot to be lost.
Compulsive liar.
I didn't say that.
I just thought I'd
confess. But I didn't think there was much to be gained from me trying to translate John. Instead, I sort of tried to capture him on the page. But I thought today we could just sort of, in talking about the process a bit, really just talk about the arc of your career. But first, I'll just mention that I came to John through my first book, which was about Donald Coxeter, and he was born in London and was at Cambridge from 1926 to 1936, and then he went to U of T and was in Toronto.
Incidentally, Richard Guy and I were once travelling to that well-known Canadian city, and he's as we were going up to the ticket desk in some airport or other, he remarked that there's only one T in Trana, and both the vowels are A's. And so I was quite amused by this, because Richard Guy speaks in what I would consider a posh English voice, posher than mine anyway. And then, you know, he got to the ticket desk and asked the girl for 2 tickets to Trana, you know.
Which is how I usually say it when I'm not taking special care
or Toronto.
To Toronto, yes, to enunciate.
There's only one T in her pronunciation, and both the vowels are O's, I think.
Toronto. So be it. But in researching the Coxeter book, everyone said you have to talk to John Conway. And you know, you're both consider themselves first and foremost geometers, and my life became totally immersed in geometry. And I guess has been for about 10 years, and this was a sign just outside a rental car lot in my hometown of Belleville. But here is his Coxeter, more or less how he was looking when I met him. And he was known as the man who saved geometry. He sort of kept the flame alive during a lull in the mid-20th century before the advent of the computer really spurred its renaissance. But everyone was telling me, so you've got to find Conway and talk to him, and it was a bit difficult because you know you're hard to reach sometimes by phone and email, and you're around and about. And I remember I found you finally at math camp, and this is roughly what I encountered when I saw you, was your sandals and shorts and having lots of fun with the math campers.
I can't see that.
Right. Yes. It's
okay. Notice there, I've got a sort of blackish beard. I hate now that I've got a sort of whitish beard. I avoid looking in a mirror, which is, you know, quite some achievement. And then when I go past a shop window and the shop isn't illuminated from inside, I have to sort of go like this so that I don't actually see this old man walking past the... Okay.
Right. Well, you were in fine form at math camp, and you know, you were quite fetching fellow, and you...
Thank you.
You're welcome.
It's not often a woman says that to me now.
But, you know, what I found was, you know, this grown man who, legendary, I'd, you know, heard all about John before going, and you very graciously talked to me about Coxeter and spoke very highly of him, but you also told me an awful lot about yourself. And so I thought immediately, aha, here is another book. And soon enough I circled back around and proposed it to you, but initially you said no, you weren't game initially, but ultimately we set to work. And I guess the crux of your career was really 1970, or this 12-year period that you call your annus mirabilis, when
no,
you...
it was only a 1-year period. This actually.
Oh, 12-year, 12-month. Pardon
12
me.
months,
Yes.
okay, yeah.
Yes. But in that 12-month period, you invented the game of life, or the climax of that, discovered the surreal numbers, and discovered the Conway group. So you had quite a white-hot period.
Yeah, it was a good year. I'm trying to think what I can say about that.
Well, you're proudest of you're a bit down on life now.
Life.
Although depends on your mood, it comes in and out. But
Hey, listen. We decided.
oh, right, bit of a paradox that he is wearing. He brought his life shirt on the trip, despite the fact that he's so.
It was clean.
Right.
Because I seldom wear it.
Right.
This is the second time I'm wearing it because I thought it would be quite a good thing to put on for this.
Yes, indeed. But you're proudest of the surreal numbers, so maybe you can tell us a bit about that discovery and how it came about, studying games and so forth.
Yes. Has anybody heard of the surreal numbers in this audience? A few people, yes. I know you have. So why didn't you put your hand up? And I know you have, actually. But yes, the surreal numbers were a very simple thing. I don't know whether to tell you how I came across them first, or tell you roughly what they are. I think I'll tell you roughly what they are in the quickest possible way first. You know, Dedekind, the great guy who sort of found a way of embedding the real numbers in set theory, describing them, did it the following way. And this is the trad way of defining the real numbers, roughly. You cut the rational numbers into two parts, the left-hand part and the right-hand part. You know, two disjoint parts, but together they make up all the real numbers. And then these cuts are almost in one-to-one correspondence with the real numbers, you know. I mean, pi, for instance, is bigger than 3, and it's bigger than 3.1, and those are bigger than 3.14, and 3.1415, and 3.14159265358979, etc. And on the other hand, it's smaller than 3.2 and various other rational numbers. And it induces what's called a Dedekind cut in the rational numbers. And I discovered, totally accidentally, I wasn't trying to do this, I was actually trying to understand the game of Go. I never understood the game of Go. But I did find the surreal numbers by thinking about them. I discovered if you omit these conditions, that you're cutting the rational numbers, and that the union of the two sets, L and R, the left and right sets, is the whole of the rational numbers, and so on. You keep them disjoint, and you keep the condition that every number in the left set is less than every number in the right set. Then, well, I define a surreal number to be one that's made like that. You take some already known surreal numbers, put some of them on the left and some of them on the right, with every left number being less than every right number, and that defines a surreal number. And there are simple rules to say when one surreal number is less than another and what the sum of two things is, you know, and so on. And so it's interesting. I said you have to have some previously known surreal numbers. So here's a test for you. People who actually know the answer already, don't take the test, please. How does the proceeding get started if you can't build a surreal number without having some surreal numbers, so to speak? Well, you failed the test. All of you. That's disgraceful. What you do is you put a set of surreal numbers on the left and a set of surreal numbers on the right. Initially, that has to be the empty set. So what you get is open curly brackets, then write nothing at all, then write a vertical slash, a down slash, then write no numbers at all, write nothing at all, and then put a closing curly bracket. That is a particular surreal number. That's the surreal number I call 0, or naught, if I'm in England. I think I am in England now. And then I won't tell you the definition of inequalities, you know, when one surreal number is less than or equal to another, and so on. But I will tell you what the definition of sum is. X plus y, oh yes, the things you put on the left are called the left options of x, and the thing you put on the right are called the right options of x. x plus y, the left options of x you use to define x plus y are the left options of x plus y and x plus the left options of y. And the right options you do a similar thing, except you have right options. And now I'll prove for you a theorem. I'll prove for you that x plus 0 is equal to x. So, what's x plus 0? Its left options are the x lefts, the left options of x, plus 0. Its right, and x plus the left options of 0. Well, the left options of x plus 0, by induction, are the left options of x. Because, you know, they were done before. It's a previous case, a simpler case. And x plus the left options of 0. Well, there aren't any left options of 0. So there are no left options of that form. So the left options of x plus 0, when you simplify them, are the left options of x. And the right options are similarly the right options of x. Oh, so x plus 0 is equal to x. Now, that's a simple proof. It's an unfamiliar style of proof. It's actually a case of transfinite induction. In transfinite induction, it's simpler than mathematical induction. You don't even need to have a base case. For instance, 0 plus 0 equals 0. I've already proved that, if you think about it. The nice thing about the surreal numbers is that every theorem is really like that. Finding the right definitions is hard. It took me 18 months to find the right definition of x times y. Anyway, I don't know whether you can tell. Oh yes, I should remark that there are many more surreal numbers than you realize. One of them, for instance, you can prove, in fact, that, well, you can, let me define 0 I've defined, 1. 1 is 0 / nothing at all. 2 is 0 and 1 / nothing at all. However, if you're greater than 1, you're automatically greater than 0 and 1. That's not obvious because you don't know what inequalities mean yet. I haven't told you, but it's provable. So if you're greater than 1, you're greater than 0 and 1. So 0, 1 / blank is the same as 1 / blank. And it turns out there's a nice theorem that everything is the simplest thing it can possibly be. You don't know what that means, but it's true. So the way to say things of the type that I'm just saying is 2 is defined to be the simplest number greater than 0 and 1. And it's therefore the simplest number greater than 1. And 3 is the simplest number greater than 2, and so on.
And John, when you talk about all these numbers that fell out, you often describe it as being like Cortez standing on the...
Yes,
what
indeed.
was the experience like?
I haven't given you a clue as to how big the surreal numbers are. I will just say a little bit about that. If you take 0 and 1 and 2 ... with only 3 dots there, / blank, that's the simplest number greater than all the finite integers. And that's Cantor's number. Cantor's name for that number was omega. So among the surreal numbers, as well as the real numbers, I haven't told you about those yet, but I don't think I will, there are some infinite numbers. It is also the number 0 / 1, comma, a half, comma, a third, comma, a fourth, comma, ... That's the simplest infinitesimal number, positive infinitesimal number. Turns out that's 1 over omega. These things are all theorems, you know, not definitions or conventions. Well, the choice of the names for individual surreal numbers is sort of conventional, and it copies the names that people have given already to the real numbers and Cantor's infinite ordinal numbers and so on. But there are so many surreal numbers, it's unbelievable. And I walked around in a daydream for ages and ages and ages. I sort of, well, as Siobhan has just sort of remarked, there's this, well, she didn't actually tell you as much as this, but there's this remark, which I think is in a poem by Keats or somebody, but which says, Stout Cortes, you know, he walked across the American continent to the other side, and he was monarch of all he surveyed. I felt a bit like that. I was getting pretty stout, I suppose, but that's not the point of the thing. I kept on thinking, my God, nobody has ever seen this before. And you discovered it, John. You discovered it. That's what the serial numbers are like. And it gave me a wonderful feeling to have seen something nobody found before. And this is, in a certain sense, the largest extension of the real numbers into a field, you know. And
so you're proudest of them, would you say? But you're also slightly disappointed that they haven't been applied,
yes,
or
I
found
am
a
very
broader.
Disappointed.
Mm-hmm.
Nobody. They are so natural that it would seem that, you know, they have some application to something.
And you went to visit Gödel to ask him. Tell us about that story.
Oh yes. Well, Gödel, the famous logician. I was just going to give a talk to an undergraduate math club at Princeton. This is long before I actually joined the faculty there. And while I was there, Stanley Tenenbaum, a strange friend of mine, said, while you're here, would you like to see God? So of course I said yes. I should explain that the sort of graduate student types in logic, mathematical logic, had names for various mathematical logicians. And Gödel, of course, was God. Kreisel was Christ. There was another mathematical logician, Alonzo Church, who was just known as the Church. And then later on, there was Eric Bishop. And he was the bishop. But anyway, that's roughly the pecking order of these various people, which was rather nice. Although one could argue about it in some of those cases, but still. So of course I wanted to see God. And the reason I think why I wanted to see God was that in his paper, which I thought was 1944, but I don't think it was, somewhere around that vintage anyway, called What is the Continuum Problem? Or what, he says, maybe we'll only know the proper solution of the continuum problem when we have the correct theory of infinitesimal numbers. And I sort of thought, with some justification, that I had the correct theory of infinitesimal numbers. So I was keen to ask him, what did you mean, you know? So I summoned up my courage. I was overawed by the man, you know. Whenever you meet God, you can't just sort of take it lightly. Well, so, you know, I tentatively asked him at the end, what did you mean, you know? And he said, oh, did I say that? Well, I was mistaken. Which sort of depressed me a little bit, you know. Anyway.
And then more recently, something that you're also very proud of is the free will theorem, which you've done with Simon Koshin at Princeton. And I have the compound of three cubes, which you use to describe.
Oh, I can see that. I don't have to turn around.
Oh, good, there. So maybe tell us how that came about and how long you were working on it with Simon.
My colleague and friend Simon Koshin in Princeton, who was educated both as a mathematical logician and he was also well educated in quantum mechanics and so on, physics in general. He and I were discussing, well, this sounds very falsely modest, let me say. We were discussing how the world works, you know. What I mean by that is we were actually trying to understand one particular famous quantum mechanical experiment, which is called the Stern-Gerlach experiment. Well, actually, we discussed an electrical modification. The Stern-Gerlach experiment uses magnetic fields, but there's an analog of, and it's well known, there's an analog of it which is less well known called the Vrede experiment, which uses electric fields instead of magnetic fields. And the thing about this is that, well, these two experiments really are, most people will have heard the remark that quantum mechanics does not predict exactly what particles will do, you know. And it only predicts probabilities, they say. Koshin had a theory that he was talking to his friend Jim Axe, who was his collaborator in proving this, in elaborating this theory, that sort of purportedly did go beyond quantum mechanics in sort of providing such an explanation. Anyway, we were discussing this thing, and my contribution was not understanding quantum mechanics. In fact, not understanding probability. You know, I remember attending a course called Random Variables in Cambridge, and after about 5 lectures of this 20 lecture course, or 16 or 24 lectures, the teacher, the instructor, whatever, defined a random variable to be just a variable. Well, he did say some other stuff about it, but it was a variable for which you had a probability distribution added. But you know, I don't understand what probability means. I still don't understand what probability means. I'm a sort of professional understander. You know, I learned enough about probability to answer the examination questions and that sort of thing. But you can often do that without understanding really what it means. And I like to understand what things mean. Anyway, so you see, you have very little hope in understanding quantum mechanics if you don't understand probability. I did want to understand something about quantum mechanics, very much. I attended a lecture course given by Dirac, actually. By the way, that was rather funny. It was in Room A of the art school, and most of the students sat from row 5 and upwards. I sat in the front row. Dirac was a mumbler. He seldom looked at the audience, so he mumbled into the blackboard. I could just about hear him. Every now and then he did look to the audience and then quickly looked away because he realized there was an audience there, you know. That made him nervous. Anyway, so at the end of that course, I did enough to pass the exam, just about. And then I decided not to try to follow that, you know, academically. But I still really wanted to know what it was all about. And every now and then I would read the Scientific American, some article about QM, some new effect, you know, some new mysterious effect. I never felt I understood it. I still don't feel I understand it. But with Koshin we proved this free will theorem, which doesn't really involve the notion of probability at all. But it does use some bits of quantum mechanics. It uses some bits that I can understand. I don't think I'd open up that can of worms just now, but I'll be happy to if somebody wants to talk privately about it. What we proved is that if three particular things we call axioms, which are taken from quantum mechanics, QM, and relativity theory, it doesn't really matter whether it's special or general relativity, hold. And if in addition we human experimenters, I'm not really a human experimenter, but never mind, have free will, have a little bit of free will, one binary digit of free will, then so do the particles. And that's really quite, and what do I mean by free will? Well, look, I don't believe that that action was determined by the state of the particles in all the universe at the time of the Big Bang. It's possible as it was, you know, but I find that too big a thing. I think it's really rather an amazing assumption that the world is deterministic to that extent. What we prove, yes, okay. So that's what I mean by the fact that I have a bit of free will. Oh, let me just say what we suppose, a bit of free will. If the amount of free will I'm supposing that humans have is the ability to press either the red button or the green button on some piece of mechanism. In other words, to take a binary, well, I was about to say to take a binary decision. However, to perform a binary action independently of the entire past history of the universe. Binary decision sounds pretty small. Independently of all that stuff sounds pretty large. However, you know, I think the opposite sounds larger, really. And what do I mean for particles to have that? Well, the particle can emerge along channel C or along channel D in a manner independent of the past history of the universe. If you do suppose that human experimenters have that binary possibility, then the particles have it too. You know, people object to this. They think, oh, free will involves much more than that. That's really because in philosophical discussions, the idea of free will, how can I say it? It's all bound up with questions of moral responsibility. You know, you don't want people to be able to get away with murder by saying, oh, I didn't want to do it, but it was determined, you know. So you want them to be responsible for their actions. But what I'm supposing when I talk about pressing the green button or the red button is, well, has no great moral consequence whatsoever, you know. If you press the red button, nobody dies, you know, as distinct from the green button. It's just an unimportant action. Anyway, and the three axioms we take from physics are, we call them spin, twin, and fin. The spin axiom says that in this experiment I was talking about, it's called measuring the squared component of spin, which from now on I'll just say spin, of a particle in a given direction. And it says that if you do that in three orthogonal directions, well, first of all, there's a technical thing, they commute, which means it's possible to do it in three orthogonal directions. And you always get two ones and a zero. And that follows from quantum mechanics. And it doesn't really involve probability. It does slightly. If you do this thing 1,000 times, then you probably find you get 2 ones and a 0 999 times. The probability isn't exactly 1. I mean, you probably, you couldn't sort of blame that on the fact that your 3 axes weren't orthogonal. One of them was only 89.99 degrees or something. So it really involves the notion of probability, but very weakly. If a probability is very, very nearly 1, well, I feel I know a bit more what that kind of probability means. So that's the spin axiom. The twin axiom is this thing that some of you may have heard of it, the Einstein-Podolsky-Rosen property, that says that you can produce a pair of particles. But, oh, by the way, this is a spin 1 particle, I should have said. You can produce a pair of particles, spin 1 particles, that have effectively been twinned, meaning that if you do this spin measurement on one of them, if you make exactly the same measurements on the other one, then you get the same answers. But it doesn't matter how far away those particles are. And this is a rather strange thing, which if you read descriptions in sort of popular physics books trying to explain QM, they tend to say something that's obvious nonsense. That I measure this experiment here on Earth, measure this particle. Somebody else measures the twin particle on Mars, which is always at least 5 minutes away, 5 light minutes away. Then they sort of think, this measurement, I will know what my colleague on Mars is going to measure, if he does this experiment. However, it's symmetrical. If I do this measurement, let's say at noon, simultaneity doesn't mean anything precisely, but it means it fairly closely. We set our watches, we synchronized our watches, and then he went off to Mars, not going near the speed of light. But anyway, if I make this measurement, they say, that instantaneously transmits, sets the other particle. But that's nonsense, because instantaneity doesn't mean anything in relativity. What happens is, if he makes the experiment after me, then he will get the same answer as I've just got. But if he made the experiment before me, then he will have got the same answer as I just got now. Notice that that remark is independent of simultaneity, really. It doesn't matter who you consider as first. So it's obvious that neither experiment sets the other one. They're just correlated. Careful physicists make a difference. I'm sorry, that perhaps I should shut up about that.
Well, it's interesting because it's it's a very heady subject, if you will, and I'm always a bit comforted that even Simon and John, when they're discussing it, and they continue to discuss it in Princeton, and you may write a book together, but you're always acknowledging the sort of ineluctable nature of the subject, and that you're still grappling with it. And I guess in general, just to talk a bit about my approach to the book, and John mentioning that he's a professional non-understander, that's also something I found very reassuring, because I don't have a mathematical background myself. My background is in history and journalism, but I'm attracted to mathematical and scientific subjects.
You're an amateur non-understander.
Yes, right. So John was extremely generous in talking at length about these subjects, and in particular the free will theorem was probably I wrote a number of articles along the way, and that was one of the first pieces I wrote for a national newspaper in Canada, the Globe and Mail. and that was almost in close collaboration with you and Simon, because it's, you sort of have to fact check these things, and you have to simplify and distill down the ideas for the popular science reader, but you don't want to totally bastardize the truth of the matter, or the essence of what's being talked about. So it was just I guess your approach to mathematics and science in general was something that I found very open and sort of flexible, and you were willing to entertain my stupid questions. I mean, they say there are no stupid questions, but I mean, I asked such simplistic questions. So it was an interesting back and forth, and the free will theorem sort of frames the book, which is divided into 3 parts. And so the part 1, 2, and part 3 all open during a magnificent lecture series that John gave in Princeton. It was a public lecture series of 6 lectures on the free will theorem, which drew packed houses of, I think there must have been 600 or more on the first night, and the numbers kept up there until the end. And it was a nice frame for the book. And are you still planning on writing a book with Simon?
Yes. Here's the trouble. The reason I walk with this cane, limping along, is that I had a stroke. This course of lectures was advertised to be in McCosh 50, Princeton's largest lecture room, which is a rather old room. And if you arrived there on the day the first lecture was to be given, you just saw a piece of paper saying postponed until further notice or something. And then I actually did get round to giving these lectures, and those are the lectures you were actually talking about. I think it was 2 years later. And by that time, the heat had gone off, so to speak. I don't suppose that made all that much difference. The lectures were given in a more modern room. In fact, they were given in 2 rooms, so it was an overflow. Yes, they were sort of quite interesting, but I'm afraid the heat went off in another way too. I could no longer type very easily. When we tried to write this book, when we started, which was before this stroke, Simon and I would discuss things, and then I would type, a version and maybe edit it and so on. I can't really do that now. The reason is, irritating little thing, which is not the stroke, but the little thing called the TIA that came after the stroke, and it's deleted the left-hand half of my left eye's circle of vision. What it should see is roughly a circle. I actually see what's to the right-hand side of a vertical line bisecting that circle. If I close my right eye now, I appear to see a complete circle, or very nearly a complete circle anyway. In fact, I don't see that. If I do this experiment, I see the finger. Oops, don't see the finger? Do see the finger. If I do that experiment at a lot of different heights, I can work out that what I actually see is a semicircle, not a circle.
Well, maybe you'll get to the book still, nonetheless.
Yeah.
I thought maybe we could talk briefly about another subject that sort of still leaves you a little confounded, which is the monster. And you wrote the monstrous moonshine conjectures with Simon Norton, who's here. And you sort of always say that you still want to understand why the monster exists.
Yes. Incidentally, we did the moonshine conjectures to a certain extent without Simon Norton, which was very interesting. Simon Norton, who's the gentleman sitting here, he arrived at Cambridge at a very early age, already with an external degree from London, and started sitting in at Part 3 lectures next to me, and then we got all interested, I mean the other people got all interested in playing backgammon, and Simon had played backgammon with his brother earlier on, and he moved much more quickly than we could, and he did everything more quickly than we could, you know. So what was I going to say about that? So a lot of our discussions, and we and our in that refer to all what we call the groupies in Cambridge. That meant the people who discussed finite groups, and while Simon, what happened typically was that Simon would say something to me, and I would have some difficulty in understanding what it was. I knew it was true. You know, there's a game called Simon Says. Whatever Simon says is true. Then I would explain it to the other groupies slowly. I could work out what it meant somehow. On the occasion we found out these things called the moonshine conjectures, that's my word for them, Simon was away, doubtless travelling on trains or buses, because he's very fond of those things. And that was lovely, because when he came back, we'd already made quite a lot of progress. And so for once, we were ahead of Simon, and were patiently explaining to Simon what had gone on. The one time, as far as I remember, when that happened. Anyway, that was very pleasant. But in the end, Simon and I wrote the paper on moonshine. Moonshine was my name, I think, probably. Monstrous Moonshine, we called the paper. It was the following thing. This will be incomprehensible to many of you, don't worry. We had just received, we were working on a book called The Atlas of Finite Groups, and we were working on these character tables of finite groups, and we had the character table of the monster, which is, it's again my name actually, which is a very, very large finite group. And the smallest dimension of space in which this monster acts non-trivially is 196,883. You know, the usual way of representing groups, well, there are two of them. You can represent it as matrices, in which case there have to be at least 196,883 by 196,883, or as permutations on n letters, in which case n has to be at least some 20-digit number. So those are really very hard. It's very hard to sort of hold the monster in anything, even now. A student of mine, Robert Wilson, worked on this for some time and found a way of essentially containing one element of the monster and even multiplying it by another, so you have to have the other. Anyway, it's very, very difficult to work with the monster. I've forgotten how I was going to go on with that. I'd better go find a quick thing. Oh yes, 196883. There's a classical, very famous group, the modular group, which is a group that just acts on the complex numbers, or some of them, it's invariant under adding 1 to the variable, and therefore it's, in other words, a periodic function in particular. And a periodic function has a Fourier transform, Fourier series, and the coefficients of this series for the elliptic modular function, called the J function, begins 1 over q plus 196,884 q squared plus dot dot dot. Actually, there's a Q term too, but sorry, no, plus 1968884Q. There's a constant term too, but that's nonsense. I mean, John Mackay noticed that 196884 is one more than 196883, and well, he noticed one or two more things. The things that we all got so interested in when Simon was away was understanding what that was. It set up a whole series of relationships between the monster character table, which was hot off the presses, worked out in Birmingham, by the way, and this good old classical piece of analysis and geometry and a few other things, which dates back to at least to Jacobi's Fundamenta Nova Functionem Ellipticarum, one of the last books written in Latin, last mathematical books written in Latin.
And you said when you went to find that book in the library, you were looking up a number.
Yeah, and then we found that all sorts of other series were closely related to the monster character table as well. And we wrote a paper called Monstrous Moonshine. The reason is it didn't contain any theorems. It seemed to be illegally distilled, so to speak. Here were these relationships which we couldn't prove. They obviously meant something, but it didn't seem to be quite a legal mathematical paper. It's been cited rather a lot, so mathematicians quite like it. Physicists like it too in some ways. Anyway, so I think that's Monstrous Moonshine. I would like to understand very much why the monster group exists. I've been saying that for a long time, ever since we worked on the monster, in fact, and I don't feel now that I will succeed in doing that, but before I die, because I'm 35 years older than I was when I sort of first thought about this problem. And haven't made all that much progress, but about every 5 years I've taken down the problem of understanding the monster from the shelf, so to speak, brushed the dust off it, tried to discover something, and usually discovered something about the monster, but not sort of why it exists, something more to be explained usually. You know, a period of 5 years, there's an English word, lustrum, which means a period of 5 years. I've seen it used in 2 English books. One was Benjamin Disraeli's Sibyl, but a young man is described as not having entered his 6th lustrum yet, which means he wasn't yet 25. And then another thing is a detective story by A.E.W. Mason, but never mind. So it does exist in English.
Is there a third book?
I don't know. Do you know one?
Well, it's
I can see it.
Sorry?
I can see it.
Oh, I see. Oh, yes, but then.
But this is a good idea. This is a good example of John being a word nerd. And before we can open it up for questions, but I thought I might just relay one nice anecdote, which really for me encapsulates the experience of writing the book and spending upwards of 10 years with John on the brain and in my company. I interviewed John. Was sort of the only primary source. You've kept no archives, so I really had to talk to the man quite a bit. But I also interviewed a lot of people, and many people here at Cambridge were very generous with their time. And I interviewed people at Princeton, and Peter Sarnak, who's both at the Institute and at the University in Princeton. I asked him how he would distill Conway if you had to sort of reduce it to one word, and he said, well, he's a seducer. And then he sort of thought, well, no, he's the seducer. And that I thought was a fairly apt description, because
What did I tell you about seduce?
Yes, I'm getting
Oh,
to that
okay.
point. But when I was here, I learned that there was something called the John Horton Conway Appreciation Society. Although I could never find I couldn't find it in the books anywhere. But I was assured that it was something that existed in the concrete, and that everybody that thought Conway was a good thing automatically belonged. But as John was suggesting, when I put that nice little tidbit from Sarnak in the book, and John read the book, and of course was tremendously pleased to be called a seducer.
A
And
bit embarrassed.
but he promptly schooled me on the etymology of the word. Do you want to do it, or shall I? I mean, the root deuce or duct, meaning to lead, and we happen to be on a
Dupere
train.
in Latin.
We happen to be on a train
You
to
have
Math
a lot
Fest.
of juice words or duct words in English coming from this thing. There's reduce, dejuice, e-juice, seduce, conduce, conduct, and so on. The Latinate etymology of English is really quite easy to learn. You have about 20 simple verbs and about 20 prefixes. And so you just learn what the 20 prefixes mean and what the 20 verbs mean, and you've learned 400 words roughly. And that's nice. And so conduce, conduct, is to lead together. Reduce is to lead back. Well, I won't tell you them all. Seduce is to lead astray, and so on.
And that was a fairly apt way to describe my experience on writing the
led
book.
you astray.
Yes, in a good way. Yes. So maybe that's a good place to conclude, and we can open it up for questions if people have questions for John. Or
Can I say to everybody, in case you drift off before the end, that on Thursday in this room, John Conway has agreed to give a lecture entitled Surreal Numbers. That'll be a mathematics talk in this room next Thursday between 3 and 4.
Yeah.
very nice. The more
I've also not only agreed but more or less forced another lecture to follow that after a suitable interval for refreshing oneself or something, or relaxing, on I don't know how to
well, it's on your most famous or your most successful talk.
well, it's my most successful and funniest talk ever. That's perhaps all I should say about it.
So questions? Does anyone have a question?
Okay, well, we're finished then.
Okay. Terminological question. If I remember correctly, surreal numbers were originally known as numbers.
Yes,
Uh,
I can
the
talk
first place
about.
I've seen surreal is in, I think, something down Knut Road.
Yeah, that's
Is
right.
that the correct history? And if so, how did you
Yes.
react?
Well, I did a really stupid thing. I thought that if you put an adjective in front of number, you restrict the class of numbers you're talking about. Prime numbers, not all numbers are prime. Rational numbers, not all numbers are rational, and so on. And I thought that, it was better, therefore, not to put an adjective, since this was a very large set of numbers, in fact, a maximal set of numbers. That was a bad career move. And I'm usually pretty good at inventing words for things, and just to call these things numbers, well, that wasn't my invention, it was my silly idea for naming them. And Donald Knuth, well, I gave a lecture in his house, actually, in Palo Alto, and overlooking the bay, a very nice house. He was very taken by this, and then he wrote a little book called Surreal Numbers. Actually, it's interesting how he wrote it. His wife is Swedish, and so they went to Stockholm, and then he didn't entirely relish the idea of having a lot of people talking Swedish all around him, although he knows some. So he took a hotel room in some hotel in Stockholm, and he described it as having an affair with his wife. He would work on the book until about 2 in the afternoon, and then his wife would come round and they'd work on other things instead. And then, the same thing would happen next day and so on. And in a week, he essentially wrote this little book. And she illustrated it, by the way. And it's about 2 people, I think they're Alice and Bob, who are on some kind of island, and they dig up a stone, and it says something which is written in rather Old Testament sort of language about how J.H.W.H. Conway discovered numbers. It's really rather appropriate because the surreal numbers, you start from nothing at all, and there's an instantaneous sort of creation. Okay, so that surreal numbers are a very good choice because they are above the real numbers, and they are a bit surreal or bizarre, and so I should have invented that name or discovered that name, but I didn't, in fact.
Are there any other questions? There's a question over here somewhere.
Can I ask about, so part of this talk was about the process of biographizing John,
Yeah.
and I'm interested in the lovely chemistry to see between the two of you, and you're mockingly calling John a know-it-all at the very beginning.
Right.
And I'm wondering, have you
I don't
had...
think she was mocking me.
He is.
I am a know-it-all. Yeah.
Non-deference, let's say that. Have you had similar relationships in the other people that you've done biographies of, or is this a particularly unique relationship?
No, I think this is an entirely unique relationship, and partly it grew out of the length of time, the amount of time that we spent together, and
Too long.
too long. But no, I mean, he's a fascinating person to listen to, a fascinating storyteller, and there's so many interesting ideas which I really do struggle to understand, not being a mathematician, as I said. But yeah, it was a good mix of someone who loves to talk, someone who loves to listen, and we just sort of explored these ideas, and it's a chemistry that worked.
Thing about strapping a pig down or something.
Oh yes, there's a tradition in. I was at the Institute writing the book, and there's a history of science department there. And I had lunch with Heinrich von Staden one day, and he was writing a paper about this tradition of vivisection. I think it was in the Middle Ages, and they would strap a pig to a plank and cut it open while it was live, and to study the internal workings of the pig. And in the prologue to the book, I suggest that maybe was a little bit what the process was like for John, to be sort of strapped down in the armchair, and I prodded him with all these questions endlessly, and then you saw it on the page, which I think must have been a little bit uncomfortable, but I have to say he was quite gracious and didn't throw too many tantrums.
Gracious.
It surprised me where the life game, he didn't want there to be too much about life in there, and but you didn't cause too many problems, so that was helpful.
Yes, I am the biography, where ends with a double E. And I just came across or invented another word like this, which is rather nice. Well, this is an inchoative noun actually, but inchoative really means coming into being. And the word I'm thinking of is somebody who's being knighted is the knightee. I like that. That's distinct from a knighty.
Right. Mm-hmm.
Just the way biography is distinct from biography.
Mm.
I hope you detected the spelling there.
But no, I didn't have any kind of similar relationship with either of my previous subjects. So it was entirely unique.
Coxeter was interesting. You know, Coxeter was my hero in a way in geometry. And he was a very interesting man, but a sort of, I don't know,
he was sort of a proper Edwardian gentleman, yeah. He's very reserved. But he was at the end of his life when I got to know him, and it actually got to be a bit of a, you know, his daughter was taking care of him, and so I would go and do interviews with him when she needed to, you know, get out and go and see a movie. So it was almost a bit of a caregiving role in that case. But I think that happens when you spend so much time with a subject as a writer. You develop these relationships, and you have to sort of balance, you know, the relationship with objectivity and, you know, try and maintain some distance. But at the same time, it's a good idea to like the person, the subject that you're writing about. Otherwise, it would be quite an unpleasant experience. And so I definitely enjoyed spending the time with John, and I learned an immense amount. And
unpleasant experience was mine.
Ouch. Are there any other questions? Yes?
You give a very nice impression of mathematics. The creation of mathematics is always a playful exercise, one that's entirely enjoyable. And I think some of us in this room will find that from time to time we come across great difficulties that are totally obsessively depressing, and but
yes.
I don't get any sense of that in the way you speak.
Well,
about
stick with me, babe. I'll try to make it not so depressing. I mean,
yeah, but is it always, I mean, do you have the view of Hardy that mathematics should be enjoyable and playful and elegant?
I have almost always enjoyed it. You know, I was a sort of good student when I was a student here, and you know, at various times different things have happened, but usually it's been some other reason. You know, I have been very depressed at various times, well, I like to say, you know, I've made some bad decisions in my life. I should never have married that woman. That's the kind of decision that I've made bad ones. Mathematics has always, for me, been a sort of anodyne thing. You know, I can a sort of calming influence sometimes, and on occasion, on the best of times, far from calming, a white-hot feeling, you know, when I was on the point of doing some really great discovery and I couldn't sleep. Those white-hot periods, well, first of all, they don't come nowadays. That's really rather sad. I wish they would. On the other hand, I'm actually writing more papers now than at any previous stage of my career. That is largely because I have this friend Alex Reber, and he's very interested in mathematical. He's actually a professor of computer science, but he did a mathematics degree in Cambridge sometime after I did, and every now and then we're having a mathematical conversation, and he says, "Is this yours?" You know. Many times I say yes, not every time. And then he says, knowing the answer already, he says, and did you write it up? And then he says, well, after he hears the answer, he says, well, let's write it up. And so I'm writing more papers now with him. Not always, he's very generous. Sometimes he's a co-author, other times he's just an amanuensis. They're not as good as the papers that made me famous mathematically. Mathematicians don't get very famous, but I'm one of the famousest. But they're pretty damn good, and I still enjoy mathematics. I still enjoy teaching mathematics, and I suppose that's answered your question. I can't remember what the question was. Probably have.
Except for the question about utility. Does matter. What is your
Oh,
how you stand
utility.
with utility?
Oh, that's interesting, yes. So I suppose it's like Hardy, yes. I mean, he had the idea that any mathematics that was applied, so to speak, to a problem well, let's say, is boring. I find that in some ways, namely, well, here's something that often happens to teachers of mathematics. We teach something, and they say, the student says, when are we going to use this? You know, and they think they're interested in the uses, and they're not. They really aren't, because you know, if you give them some uses, they're just yawning. Because the uses are less interesting. You know, the puzzles are more interesting than anything called work. Anyway, so I don't know. I mean,
You mentioned your disappointment that one uses surreal numbers.
yes, that's the paradoxical thing that I was sort of going to go on. You know, there's one of my things with Neil Sloan that in a sense has been applied. We got a patent for this way of decoding things, and I'm very pleased at that. So I'm not entirely convinced by my own argument. You know, the applications are less interesting. And with the surreal numbers, it's so natural, they are so natural, that I feel that there must be a way of applying it. I think that way of applying it is inside pure mathematics. So it's not a sort of terribly practical application. The monster is also very natural. It is the symmetry group of a certain kind of conformal field theory. I don't exactly know what a conformal field theory is, I know roughly. But it's not, and it sounds as though it's a physical application, but it's really not, because it's a baby conformal field theory. So the monster is nearer to the real world, so to speak, than the surreal numbers, which of course are in the surreal world. I don't know. I was very, very pleased to be co-discoverer of the free will theorem. You know, part of that thing was the following. I told you I used to read the Scientific American articles in a belated attempt to understand quantum mechanics after I left Cambridge and so on. Understand quantum mechanics. I never really did that, but I started talking with Simon Koshin when I arrived in Princeton, and he understood a lot more of quantum mechanics than I did, and is the half-discoverer of a thing called the Cauchy-Specker paradox, or the Cauchy-Specker theorem. And our free will theorem is based on that. And you know, I feel now that I understand a little bit more of quantum mechanics and associated physics, and that pleased me. So it's, you know, I mean, these applications are sort of hanging nearby. I'm very disappointed that the surreal numbers haven't found an application. I feel that they will. It's the sort of thing that I feel, oh, probably in 200 years it finds an application, but somehow that won't satisfy me for obvious reasons. Yes, I mean, the joy of understanding something is tremendous, especially for a professional non-understander. I mean, it meant, you know, I cleared away probability from this particular quantum mechanical thing. I remember giving these lectures in Princeton, and there was a fairly well-known physicist in the audience, Frank Culler-Price, and you know, after having given the argument, I said, look, it doesn't involve the use of probability. What do you think of that, Frank? He was in the audience in the first 3 rows or something. And he said, I can't imagine quantum mechanics without probability. Well, I had to, because I don't understand probability. And, you know, that was a really important thing about the free will theorem. You couldn't prove it using a little bit of quantum mechanics that I did manage to understand, which meant it didn't involve any probabilities. Incidentally, Eugene Wigner, when Simon Koshin was, well, they were discussing appointing Simon Koshin as a professor in Princeton a long time before I went, said, oh, is Koshin the Koshin of Kochbecker? We must have him. And, you know, he was the, in a way, the critical voice, because, sorry, I don't mean critical in the sense of criticizing. He just pushed the committee to appointing Sam. There was some discussion before that.
Now, are there any other questions? Okay.
On the question of fun and potential usefulness, I have a memory of a talk you once gave many years ago, in which you demonstrated the operation of the hydraulic binary computer.
Winnie.
That would be Winnie, yes.
Sorry?
Winnie.
Winnie, is it called Winnie?
It was called Winnie, yeah.
There's Winnie.
Oh yes, that's
Where is
the
it? Oh yeah. That's me,
Device.
by the way, that handsome young man sitting there.
I remember you.
Oh really? Okay. I
on
suppose
a
you were a handsome young man once too. Forgive that.
Yes? A question over here? There's a question here.
Thinking about your remarks on surreal numbers and the free will argument encourages me to think along the following lines, and it's this. Something's holding quantum mechanics up. Obviously the basis is right. If one generalizes some of your thoughts over quantum mechanics and possibly say problems that come up in quantum computing research or modeling black holes in cosmology, what you say could extirpate probability and reinstall what Einstein might have thought was a much more classical way. But then my point is, one could think of remodeling whole areas in the light of what you're saying. I just wonder if anybody has done that. And behind that is a thought I have that the deeper we get into these things, pure mathematics becomes, forgive me using the term, more surrealistically ontological, in fact. And what may be holding us up partly is that people aren't realizing how near being a model for the actual world or ontology some of the deeper areas of.
It's interesting you should talk like that. I mean, ontology is a perennial concern of mine. I mean, the things I tend to think of, in what sense do they exist, you know? Well, you know, this happens. I'm sorry, I'm not directly addressing you. I'm sort of talking around you in sort of neighbourhood region. Well, you know, I often think of cats. Cats definitely exist, and the reason I really know that is because if you push a cat northwards, it automatically pushes backwards, southwards. It doesn't want to do what you want to do. It automatically resists it. Walls have the same property. Little children don't scream at walls, although they scream for their mother when they don't want something. They scream at their mother, I should say. They've discovered that screaming at walls doesn't work, and trying to walk through walls doesn't work either. You can't do it, so there's no point in trying.
You can do it when you're asleep.
Yeah, well, never mind. Anyway, so numbers. The reason why I sort of feel that numbers exist, even the surreal numbers, but I was particularly thinking of numbers like 2 and 3, is because they won't do what you want them to do either. You know, and incidentally, I don't think they're concepts. People often sort of misuse the word concept to mean something abstract rather than physical. Or, well, I mean, well, two is not a concept. I mean, to have a concept, you need somebody to conceive it. And by the way, the word conceive is very interesting. It sort of means getting it together. When a woman conceives, she gets it together in her womb. When a concept is conceived, so to speak, the conceiver gets it together in his or her head, you know. Anyway, never mind that. But I know that 2 isn't a concept because Mars had 2 satellites, Phobos and Deimos, long before there was anybody to have a concept of it, of this thing. So 2 really, in a sense, has an almost physical thing. And again, though, I mean, it won't do what you want it to. When I found the surreal numbers, they won't do what I want it to either, what I want them to. They'll do what they do, you know. Significant mathematical ideas are not concepts. They're just abstract. That doesn't mean that they don't exist. I mean, the ones that have very definite properties and don't have various other properties, they exist and they're telling you the way the cat does. I think that's a nice observation, you know. I mean, I've wrestled with the existence, the ontology of the things I'm thinking about really rather a lot. You know, there are more ordinal numbers, Cantor discovered the ordinal numbers, than there are points in space. How can that possibly be? You know, points in space, if space is, you know, some finite dimensional topological manifold, roughly, how can we conceive of, I don't know, we did. Cantor did.
Did you have a follow-up?
Could I probe a bit more? If we've wrongly marked what a priori is, and incorrectly demarcated that between empirical, and behind that is a presupposition going in physics, what what is this stuff? It's strange, it's weird.
Yeah.
Together with the following point, that where do we get reasoning from? Now, you know, with new stuff from since 1963, the ZF calculuses and how they solve problems, they don't. We're back to square one in a way. What I'm trying to say in that third presupposition is that we aren't very clear about the relation of reasoning and rationality itself to maths. They keep saying be rational in maths. What does that mean? What I'm trying to say is that it highlights, I think, the depth of the difficulty that you're talking about, because we may not know the border between a priori and ontology itself.
Yeah.
And I'm not being philosophical, I mean
No.
precisely what you're saying.
You know, I often think of Euclid in this sort of connection. Euclid's book is very strange. It sort of tightens up geometry. I'm not discussing whether geometry is in accordance with the physical world or not. Euclid tightens up Euclidean geometry, let's say. But it's a house based on sand. You know, if you look at the first few definitions, and I'd like to put that in quotation marks, of Euclid, you know, a point is that which hath no parts. Okay. A line, something about lying evenly between. They don't really mean anything. They have a vague significance, you know. And but then, after a bit, well, you do what I call swallowing the worm. You know, there's this indefiniteness and so on, and the start of a theory has this awful, well, use this word ineluctably. Ineluctably means, ineluctability means that you can't struggle out of it. You can just, I don't know, you can make noises. There's a certain ineffability. Yes, well, I'm faced with this all the time, really. I mean, I don't know whether you've noticed that, you know, this kind of thing is there in the surreal numbers. It's there in the free will theorem. They are hard to get going, you know, and there's this floppiness or sandiness in the original thing. But then after you've started building your house on sand, it sort of gets firmer, and you can live in it, and you can hammer, you know, things to support your pictures on the wall and so on. You know, the definiteness, the concreteness grows. Well, I think that's, you know, a property of examining a sort of new subject fundamentally. And I like doing that. What you get taught is the subject when it's already gone on for some time, and then with any luck it gets known to some extent to the general public, like probability. But look at the definition, so-called, of probability. You know, an event has probability 2/3 means, well, roughly, that if you do the experiment, whatever that means, 1,000 times, then about 660 of them times it will succeed, and so on. Do the experiment 1,000 times. What's the experiment? The same experiment 1,000 times? Well, you can't step into the same river twice, said Heraclitus. And in quantum mechanics, that's a real difficulty. If you do experiment A, you can't say what would have happened if instead you'd done experiment B. You did A. That's the end of it. If you have a theory already established, like Newtonian mechanics and dynamics and so on, then it is meaningful. Suppose I threw the ball against the ceiling with such and such a force and so on. Newtonian mechanics tells you how long it'll take to hit the floor and all that sort of stuff. And if instead you threw with twice that momentum or something, then you get different answers. These counterfactual things, we did A, but what would have happened if we'd done B? They are only meaningful if you have a theory, a sort of complete theory, and we do not have that in quantum mechanics. By the way, I should say something about Einstein's famous phrase, "I cannot believe that God plays dice with the universe." Sometimes he used "I cannot believe that the old one plays dice with the universe." One of the things that Koshin and I discovered, and it's a very easy argument, is that randomness is not the opposite of determinism, and which is often regarded as. And this is interesting. Even if God did play dice with the universe, that still would not explain the way the universe works. That's interesting. The precise theorem is that if the universe were to act in accordance with deterministic laws, except that those laws, random numbers are injected into the universe, all over the place, if you like, and the particles can hear them and maybe we can't. That sort of circumstance still does not enable you cannot simulate the universe based on that. And I'll give you the argument. It's very nice. I love it because it's tied together with backgammon. I mean, I call this the backgammon argument. Backgammon is a game in which the legality of a throw, of a move, depends on what the dice say. Okay. Now, I believe that historically, when you had backgammon tournaments, you had, say, 50 tables with a backgammon set on each one and a pair of players. And let's suppose it's already decided who moves first at each table. Then, originally, the tournament director throws dice and says the first throw is a 5 and a 3. And at 50 tables, the person to makes a move that's legal if it's a 5 and a 3. Then he says the second throw is a double 6 and so on. This reduces the dependence of who wins on the dice. Not quite, because there's still some dependence as to who was to move first. But anyway, it removes some of the thing. Okay. Now, it obviously makes no difference if instead of doing that, the tournament director sits up in his hotel room the night before with somebody to watch him to make sure that he's not cheating in some way, and throws the dice and notes down, the first throw will be a 5 and a 3, the second throw will be a double 6, and so on. And then he comes down next morning when the tournament starts and just reads off his last night's throws. That's very interesting because it shows that if that happened in the universe, in other words, if instead of God throwing dice now when the universe is actually working, he threw it in his hotel room before the universe started. Okay. So that says, you take the original form of the free will theorem, that says the universe cannot be explained by deterministic laws. It shows that the universe cannot be explained by deterministic laws, plus, this business about past history, by deterministic laws based on dice. Because dice are equivalent to past history. I mean, extremely past history, before the universe started. So we strengthen the free will theorem in that way. And it's a very simple argument which I like a lot, because nobody seems to have noticed before. Einstein certainly didn't notice it. Otherwise he wouldn't have made his statement about not believing that the old man plays dice with the universe. It doesn't matter if the old man plays dice with the universe. He still can't explain the universe. I think that's really beautiful. I think we're the first people to have noticed that. So, in particular, randomness is not the opposite of determinism.
Randomness doesn't cut it, is how you put it in the book.
Doesn't cut it, is what I say.
And maybe that's a good place to conclude, swallow the worm and repair out into the reception.
One more thing. I want to say, I have a proof that you can't disprove determinism. Another fairly simple argument. It's not quite on the same logical basis as various other things I've been saying, but I find it very convincing. I go to see a film by myself, and it's very exciting. I don't know what's going to happen next, and so on. And I found it very exciting. I think my wife will love that, So next day I go to this film again. And now, this I call the second time around argument. I can, from my point of view, things are deterministic. I know what's going to happen, because it happened yesterday, and I know that people don't edit movies in between one day and the next. But my wife, sitting right next to me, has the same sort of feeling, rather like free will. Not exactly the same as free will, of course, but she doesn't know what's going to happen. Unpredictability, let's call it. So, let's suppose that we're in the second showing of the Universe movie. We are getting sometime the projector went wrong or something, and now we're getting exactly the same sense impressions and everything as we had first time around. But now it's the second time around, and so it's deterministic. Now that sounds a sort of implausible story, but almost by definition you can't disprove it. We are getting, if we were getting exactly the same feelings as we got first time around, as they got, if you like, but they're us, then it really is like determinism the second time around. So we can't disprove determinism. When I was very keen on this sort of stuff a few years ago, I travelled all over the world giving lectures on it, I would ask the audience, how many are determinists? And, a fair number of hands would go up, And I think those people, perhaps I should say, were usually the most intelligent people in the audience, because it takes quite some guts to disbelieve something that the rest of the world finds obvious, And I don't think they're right, but I think they were pretty intelligent. Of course, I think I'm much more intelligent than any of them, because I've reconciled free will with physics. I think the reason why people tend to be determinists is a hangover from the days of classical mechanics, Physics was entirely deterministic for a long, long time, until 1925 essentially. And it's amazing. People found it, you know, the people who discovered the indeterminacy of QM were thought it needed reconciling with something. They thought it was very hard because they, you know, classical mechanics had got right through their heads. They were, you know, very noticeable and intelligent physicists. You know, Einstein thought this ain't what's going on, because he had been fortunate and clever enough to reform physics in a way that nobody had thought of before and reconcile some apparent impossibilities. And that was a great achievement. But his theory was still essentially like Newton's, classically deterministic, you know. And so he was sort of still wedded to this idea. His theory did not fundamentally affect the sort of basis of explaining the universe. QM did. Anyway, I'll shut up.
Well, that's speaking of the second time around, I've heard that maybe 24 times around, and it's still fairly transfixing. So with that, maybe we should conclude. There's lots of books outside, and we're both willing to sign. John does quite a handy signing job. So thank you again for coming, and hope you enjoyed it.